Support the production of more videos by visiting the Support Moof section on my website. The link is in the description below. Thank you and enjoy.
So next up, if you recall, we said that atoms of an element are defined by their atomic number, which was the number of protons that atom contained. In other words, all atoms of an element are identical in their atomic number and the number of protons, right? Those first two sentences, same thing. However, the mass number, which is equal to the number of protons plus the number of neutrons, can be different for some atoms of the same element. Okay, same element, different mass number, which means that atoms of the same element can vary in the number of neutrons they have, right? Because if the mass number is equal to the number of protons plus the number of neutrons, and the mass number can change, but the proton, right, the number of protons cannot change, then the number of neutrons must be able to change. Okay, so that's what you have an isotope. Isotopes of an element have the same atomic number, right, which means that they're the same element, but they have different mass numbers, right? So they have different numbers of neutrons. Okay, so let's consider our first example here of carbon. With carbon, there are three naturally occurring isotopes. There are more isotopes of carbon that have been synthesized in laboratories, but we're just going to consider the naturally occurring isotopes. So you can see here they all have different mass numbers, 12, 13, and 14, right? But they're all carbon, right? So the number of protons they have is equal across the board, right? They all have 6 protons, right? And I could put that 6 here, right, as the atomic number, right? So the number of neutrons they all have, we just take the mass number minus the number of protons. So 12 minus 6 in this first case give us 6. 13 minus 6 would be 7. 14 minus 6 would be 8. Now the percent abundance, basically what that is how much of the naturally occurring isotope on Earth is that particular isotope. So for carbon 12, we've got 99.89%. 99.89% of naturally occurring carbon is carbon 12, which is almost all of it. Carbon 13 is 1.11%. That pretty much accounts for essentially all of it. But in a very, very small percentage is carbon 14. Okay, so these are all isotopes of carbon, naturally occurring specifically. So a question that often comes up is, we've got these different isotopes of the same element, but how do their chemical reactivities compare, right? Do they all react different? Do they act the same? And the answer is that they're pretty much the same. They react chemically pretty much the same. And that's because chemical reactivity is not dependent on the number of neutrons. It's dependent on the number of electrons, and we'll talk more about that later. However, what they do differ in terms of reactivity is their nuclear reactivity. And that's because neutrons and protons are both in the nucleus of atoms. And the nucleus, there are certain reactions of the nucleus, that's what we're talking about when we're talking about nuclear reactivity, that can change things, right? But as long as these have the same number of electrons, then they'll react the same way. Okay. Now I do want to bring up another example just because this kind of comes up from time to time, especially in organic chemistry and some other areas of general chemistry. So we got hydrogen, okay, naturally occurring isotopes of hydrogen with mass number of 1, 2, and 3 respectively. We got protium, deuterium, and tritium, again, respectively. So they're all hydrogens, so the number of protons is the same for all three, 1. The number of neutrons will be their mass number minus their atomic number. So 1 minus 1 here is 0. 2 minus 1 is 1. 3 minus 1 is 2. Percent abundance here, 99.985% of this first one, protium. Often, sometimes, just mostly referred to as just hydrogen, by the way. Deuterium is about 0.015%, and then a really, really, really tiny amount of of tritium exists. One thing I do want to mention, though, is that deuterium sometimes is referred to as just D, right? If it's not written as 2H like this, it can be just D. That comes up pretty often in organic chemistry. And some people, surprisingly enough, don't actually know that. It's just a heavier version of hydrogen. And then tritium sometimes is referred to as T if it's not 3H, but I will say that this one comes up much less often. Yeah, so I hope that video was helpful in kind of defining isotopes and discussing a little bit about percent abundance. So thank you for watching.
If you found that video helpful, don't forget to hit it with a like and subscribe for more content. Also, follow Moof University on the different social media links in the description below. Thanks and happy studying.